Thanks very much. So, CASTAway, to break from the theme, is actually a larger spacecraft, but it has a possibility to take some CubeSats with it. So I'll introduce some of the science motivation for doing CASTAway and that spacecraft, and then go on to talk about what we can do with CubeSats. So the idea of CASTAway is a mission to explore the diversity of the asteroid belt. And the reason why we want to do this is because our understanding of what asteroids are made of at the moment has some disconnect in it. We have samples on the ground, we have meteorites, and in these we can measure composition in quite some detail, because we can take these into a lab and we can measure down to an atomic level exactly what is in here, real mineralogy. And these all come from asteroids, but as shown before, we've only visited a handful. The knowledge of the diversity of asteroids, it largely comes from ground-based observations. And from ground-based observations, we know sort of where the asteroids are. This is a distribution plot that shows the main belt, the structure in it, the resonances, and the number of asteroids we find. And we have this broad picture of what the different types of asteroids. So you've seen me mention S-types and C-types. There are some more silicates. C-types are more what's called more primitive types. So we think we have a vague idea of how these broad distributions of types of asteroids and where we find an asteroid belt link to minerals, but in only a few cases do we actually have the real link between meteorite types through asteroids and through where they come from. And so that's the bit what we want to try and understand a lot more of. And the reason why we want to do that is because if you understand this distribution of where you find certain sorts of asteroids, you can use that to lead back to try and put together the picture of how you form the solar system. These are all leftover bits from the formation of the solar system, and so mapping where you find the different sorts of minerals allows you to understand that process a lot better. So, how do we improve this link with this knowledge? Well, as I said, most of these leftover bits we think of as being broadly S-types in the outer belt and S-types in the inner belt. But more recent studies, if you start looking at distributions, that's only true in the very largest bodies, the things that we could get spectra of years ago. And as we get to smaller objects, you see that actually the mess, there's a whole distribution of different types all over the asteroid belt. But this is based on relatively small amount of information, as I'll show you in a minute. And why you want to understand this, what we have now, the distribution that you see in the current asteroid belt, is because this is the end point here of a whole lot of evolution of the solar system. This is a sketch of the sort of current popular model of solar system evolution. You start at time zero with a very nice orderly accretion disk that has rocky stuff in the inner part close to the sun, icy stuff and more volatile stuff further out. And as the giant planets form, they actually migrate. And as they migrate, they throw all the small things around, and you get mixing of all different types. You get small bodies thrown out and go out to form an old cloud and so on. Things that come in, and you get late heavy bombardment when a lot of things collide with the inner planets. And at the end, you're left with the solar system as we see it today. But there's a lot of different tweaks you can apply, and the starting point you can apply in this model to end up with what we have here, which is why we want to understand better the constraints on what we have now to fit these models. So what do we know about asteroids at the moment? Well, all of that sort of spectral type of what's where is from a relatively small amount of spectroscopy. We have only a few thousand asteroid spectra out of the almost million asteroids currently known out of the tens of millions that are out there and that we will discover. Most of this is spectra only in a visible range, so sort of this part of the spectrum. Whereas asteroid spectra aren't actually all that interesting, there aren't that many features. As you get into the near infrared, there are more features in asteroid spectrum. This is a plot showing you spectra, so this is what the actual spectrum looks like. It's mostly reflected sunlight. We divide out what the solar spectrum. You can see that different type of asteroid, an S-type or a C-type, have different reflectance spectra. They have absorption features. But you'll also notice the most interesting absorption features around here at 3 microns, which is in a range that you can't observe from on the Earth, because the grey part here is showing you the Earth's transmission windows. Most of the really interesting stuff is an area where it's difficult to observe from the ground because the Earth's atmosphere is getting in the way. So how do we improve on that? Well, there are big surveys that are coming. Gaia is producing sort of 10 to the 5 or so spectra, but again only in the visible. LSST will observe millions of asteroids, but again only in the visible range. And while with JWST we'll be able to get wonderful spectra all the way out here, we'll only be able to do that for a handful of asteroids. It won't allow you to really map the asteroid belt, which is the thing we really want to be doing. So, thinking ahead a bit to the 2030s, because if you talk about M-class missions or bigger missions for ESA, you have to think a long way ahead. What do we want to know at that point? Well, we'll want to know how do these compositions vary, not just sort of across the asteroid belt, but across different sorts of asteroids, with different asteroid sizes, within different taxonomic classes, within different orbital classes. How do they link to these meteorites? How do we really build that link to lab samples that we have? And how do we correlate the sort of information we get from LSST, where you've got an awfully large number of asteroids but limited information, with the detailed composition you can get if you look further into infrared? What evidence do we have for different history in the asteroid belt? So can we look and see mineralogical evidence for different heating, different populations? Do we understand the ages of asteroids properly? And to do that, you really want to actually resolve them, be able to look at craters and to count them. And then, how do we link all of this sort of surface properties with the mineralogy, with other various properties, like whether or not they have satellites, with their spin rates, the diagram we've seen a few times on spin rates, and whether things roll past. And what we proposed is a mission that can answer an awful lot of these questions in an efficient manner. And what it is effectively a small space telescope, 50 centimeter class, that performs a spectroscopic survey from visible out to 5 micron of tens of thousands of asteroids. So really orders of magnitude more objects all the way out to the interesting Roentgen spectrum, and really maps the asteroid belt. It also goes to the asteroid belt and resolves has close flybys with a number of objects, so you can actually get resolved spectra across surfaces as well as point source spectra of tens of thousands. And it also allows us to discover small asteroids while we're there. And the trick for doing this is that you take the small space telescope and you send it to the asteroid belt, instead of having a space telescope in Earth orbit or near Earth, where you need to have a very large mirror to be able to detect the smallest asteroids. And as I said, this was proposed for the ESA M5 opportunity for launch in 2029. The main instrument on it is a spectrograph that covers 0.65 micron range, same as the JWST one, but on this small telescope that we take to the asteroid belt instead of putting on a big telescope like JWST. It also has a CCD imager and a thermal camera which works when we fly by asteroids. And then lastly, it discovers asteroids, small ones, meter scale things that are relatively close by, actually using sort of Star Tracker technology, the sort of cameras that all major spacecraft have on them anyway, just for navigation, by tracking constellations. So, and as I said, the point of this is you send it through the asteroid belt, so we can actually have close encounters with these asteroids. On a 7-year orbit, we loop through the asteroid belt twice. This has 10 different flybys in a normal trajectory. There are solutions that find a few more trajectories. In fact, we have a whole catalogue of different trajectories, even searching a relatively small catalogue of asteroids. So we limited the search to only 10,000 or so asteroids in here, not all known ones, just to make it computationally possible. And there are already a lot of solutions. The real challenge is to find the optimal solution, i.e. the most interesting one, the one where you get the best variety of different sorts of asteroids. But it's no problem to find a trajectory where you get 10 to 20 different flybys. So, why am I talking about this at CubeSat? Well, the reason I'm talking about this is because the proposal also listed a few optional fun and exciting things that we should consider during the phase A study. One was that it'd be nice to have a laser rangefinder on it to go along with the discovery of small asteroids. That helps because you get a better range rather than just detecting them with the cameras, polarimetry elements to the camera, but then the interesting bit of saying, well, why don't we have some deployable probes that we can release in the asteroid belt based on CubeSat technology? The idea being that hopefully we could do a similar thing to the ESA token study, the AIM token study, during a phase A study. You know, have a competition, have some ideas of what would you do with CubeSats if you could launch them from this mothership in the asteroid belt. The AIM tokens thing has been mentioned a few times, so I won't spend much time on this. There were a handful of different concepts studied, probably by people in this room, that would provide a lot of different aspects to the to add to AIM. So for CASTAway though, CASTAway is designed to launch with the Soyuz, because that's what we had to do for M5, but in reality we'll be using the new Ariane 6.2. This should give us lots and lots of mass margin. So we imagine that we should be able to take a whole bunch of cubes. What can we do with a CubeSat in the asteroid belt? Well, you can release them just before the asteroid flybys. And that's the main sort of thing we were thinking about. This will allow you to get a lot closer than we would dare go with the main spacecraft. You'll be able to get high resolution views, be able to map gravity fields, maybe go and look for exospheres or magnetic fields, and then do things where you actually play with the surface a bit. There are a lot of challenges though for CASTAway. Firstly, these are fast flybys that we perform at each asteroid. The main spacecraft is going by these things about 10 kilometers a second, about 1,000 kilometers range, so the whole flyby sequence is lasting a few hours. So your CubeSats are going to be short-lived things. We're far from the Earth and the Sun, so the only way you can communicate is via relaying it via the main spacecraft. And of course, you've got an interesting radiation environment out in the asteroid belt. What can you do though? Well, firstly, you can get a lot closer. So you can release your CubeSats to just miss the asteroid, to have very close approaches. And if you got that wrong and they hit them, well, never mind, they were cheap. And so you can get a lot closer viewpoint than we'll get from the main spacecraft. You can also add to this sort of radio tracking or accelerometers and measure mass and gravity field, just from how these things move as they go past them. You could even think about things like magnetometers and look at crazy things like do these things like primordial magnetic fields, so that's a challenge. The other obvious thing you can do is you can aim to hit the asteroid. You can do impact experiments. There's been a lot of studies actually on penetrators, packing instruments into a cone that hits the surface and allows you to take a mass spectrometer or something. However, these things have been studied up to 300 meters per second, not 10 kilometers per second, so that's a bit more challenging. You could imagine a pair of cubes, one that is basically a bullet that hits it, and the second one that actually sees this, or either flies through an ejector plume or does some sampling. So concepts like that. And you can have some fun just with the actual impact itself, doing impact experiments. This is the deep impact experiment on a comet, where we blasted a hole in it and looked at the crater. It's going to be a small crater if it's a CubeSat, but that might still be interesting. And then the last concept which I wanted to mention on these is actually you can also do things with deployable CubeSats when you're in survey mode rather than flyby, where you can have a deployable camera where the view between these things would allow you to get some parallax. So this is in our discovery of these small 1 to 10 meter asteroids, which are a few tens of thousands of kilometers away from the spacecraft typically. If you have a little CubeSat release that's some hundreds of kilometers away, it gives you a parallax and allows you to measure the distances to the small things you're discovering much better. So that might also be an interesting thing to do. The challenge of this, of course, is this then is designed to be longer lived and to operate with the main spacecraft. So, in conclusion then, CASTAway, the whole idea with this is it's a very simple spacecraft that allows you to fully explore the asteroid belt and do a lot of interesting asteroid science, but is quite efficient and quite cheap by M-class standards, and it is feasible for that sort of size mission with very generous margins, especially on mass margin, so there is potential to take a bunch of CubeSats and do some more fun things with it. If you want more information on the mission that's up there, I should of course flag the one slight issue with this, which is for M5 we won't select. However, We're still talking about this because there will be an M6, and there will be other potential launches or potential opportunities, either with NASA or whoever else. We're not fussy. We think this is an interesting concept, and we'll do it with all our place. And I'll end just with the last thing, which is we do have one other mission which is still in the M5 competition, which is a completely different mission. This is a rendezvous mission to a main belt comet, a bit like a Rosetta type thing, but cheaper. And although this doesn't list CubeSats as an option in the proposal, it does talk about potential for a surface payload like an asteroid type lander. One could imagine CubeSat based on this instead. And with that, I'll stop. Thank you.
Okay, can we take some questions, please?
Just curious what the rough size of the CubeSats for your impactor concept is.
Though they are not yet really thought about. I mean, this is the whole idea of me coming here was to say we have this potential base. What will you do with it? For the impactor, you could imagine. I mean, you can imagine, and some people at the university are doing some work on miniaturized mass spectrometers or so on things for our penetrating type thing that would fit you in sort of 1U type unit for the actual instrumentation. But of course, penetrators only work on the slower speeds than we have here. So you maybe need to have, you could imagine a 1U basically block of copper. That's your impactor, and a 1U for spacecraft as a minimal thing. I suspect that just to have enough, to have add-on comms and enough AOCS ability to target, you're probably going to have another 1U.
In addition to the impactor, shouldn't you be having a sample collector really? Because an impactor can change properties of the asteroid as well, blowing it up from. So should you be collecting samples? Is that something you're looking at?
Do you mean collecting them for? Yeah. So if you have a soft lander, you could do that. But the main problem with soft lander for CASTAway is that you have to slow down from 10 kilometers per second to do a soft landing. And by the time you've done that, the mothership's gone, and you can't talk to Earth anymore. So you have, for CASTAway, you need to think of things that work on high speeds and short lived. For CASTAway, where you're dropping something from an orbit and the main spacecraft stays there, you could certainly think of more interesting soft landers, mass specs, all sorts of things.
Any further questions? No? In that case, let's thank our speaker again.